Okay, the couple questions I got on the last quizzes. Right, the last question of 12 for February 12th, and then the one for today. So, for these two, for question 2 and question 3, is it conjugated? Is it non-conjugated? What was number 2? Non-conjugated, and 3 is conjugated. Okay. So the difference here would be conjugated has to go double, single, double. Aaron? Same thing as non-conjugated, but if you put, I guess, neither of these because it was isolated, then I guess you'll have to send me an email. But that's only if you had neither of these. So, and then we'll pick up with the questions from the 14th one because that's where we need to start. So, the question about 1,2 and 1,4 products. Okay, so the last question here is, so A is either 1,2 or 1,4, and B is the other. So let me just go into that. So if it's something like this, or regardless of what the diene looks like, I'm only interested in numbering the 4 carbons that are involved in the diene system. That's what the numbers 1, 2, and 1, 4 represent. They don't represent the IUPAC numbering system of the molecule. They only represent those 4 atoms that are in the conjugated diene system. And again, this would be a bad example because it's not symmetrical. So the question is, do I go 1 to 4 from left to right or right to left, which gives you 2 different sets of products. So what I'd probably like to do is to put an extra carbon on there, so now it's identical. So now it doesn't matter whether I'm going left to right or right to left. But those 4 carbons are the most important ones, because that's where I'm going to make my decision on where to add my electrophile. Okay. So if you go back and look at those molecules, then if I added an H and a Cl to 1 and 2, and the double bond between 3 and 4 stayed the same, it's 1, 2. 1, 4 always means electrophile, nucleophile get added at the end of the system, and the double bond rotate, and the double bond moves to go between the middle 2 and 3. Aaron? Oh, somebody had a question. I thought. No?
There's no way we could have got that mixed up. Like, there's no other rational.
What a lot of people did was they numbered according to the final product.
Right.
So, yeah, it's right. So it doesn't matter, because I can show you, I'm going to show you a number of different molecules, and really it's going to depend on these 4 carbons. And so that's what we call 1, 2, and that's what we call 1, 4. I'm only dealing with this set of 4. Maybe it's a couple of points. I can go back and give everybody credit for it, but I thought I said that in the video. You know, I could just say, why don't you find it in the show me I didn't say it in the video. But then you got to go back and watch the entire thing, which I don't think you want to do.
I'll send you the snippet.
I'm fine with giving everybody credit. Some of this is built in from year to year. So, but does everybody understand now what I'm talking about with my 1 and my 2 and my 3 and my 4? Because I'm going to do, well, actually, I'm not going to do, you're going to do a molecule like that. Well, actually, we could do that one. It's pretty boring. But 1, 2, 3, and 4. So it's only the 4 bonds that are in the diene system that I'm concerned about. So that means I only add to carbon 1 or I only add to carbon 4. That's where the electrophile is going. Okay. Does that make sense? What else? What other questions did you have? Like I had a suggestion, we do 1, 2, and 1, 4, which we'll do as part of the mechanism. But I don't want to, if there's something more important question-wise. Did this diagram make a little bit more sense? I don't know. I don't think it was nearly as clean as it was the other day. But this is the energetic reason why we have 1, 2, and 1, 4. The kinetic and the thermodynamic products, if I say, hey, this is the kinetic, this is the, or if I say, what is the kinetic, what is the thermodynamic product, the bottom line is you got to take each reaction individually. But what you're going to do is remember what the characteristics of kinetic and thermodynamic are. So the kinetic product always comes from the most stable intermediate. And the thermodynamic product is the most stable product, and it always comes from, well, it always is the most stable product. Those are the two concepts you want to use. Because if I change molecules, I can change whether 1, 2, or 1, 4 is kinetic or thermodynamic. There's no rule for that. In some cases, 1, 2 might be kinetic. In other cases, it might be thermodynamic. So you've got to use just the basic principle. So for instance, let's say I've got this molecule. What?
You want to do a shift?
Well, what I'm going to ask you to do for Friday is, I'm going to say, let's react this with something. We'll use HCl today, because that's easy. So I'm going to say HCl. Now, I could ask you a number of questions here. I could say, write the complete mechanism. Both resonance structures, the resonance hybrid, tell me what the kinetic product is, tell me what the thermodynamic product is, tell me what the 1, 2, and the 1, 4 products are. That would be the whole thing, which is for Friday. Or I could just say, what's the kinetic product, what's the thermodynamic product? So I can apply it to both. Here's the products of the reaction. Here's the entire mechanism. So, can we do this? Well, what am I going to add to the double bond? H plus. All right, so where am I going to add H plus to? Carbon 1, but then I need to remember there's my 4 carbons. So I'm going to add the H plus to carbon 1. Okay? And I get that carbocation. What am I doing next?
Resonance.
Draw the resonance structure of it. So how am I going to do that? Move the double bond here. And that puts positive charge over there. Right. Next step. Do what? Yeah, we could add chloride to each one. So again, it's a little more difficult to react the resonance hybrid with chloride and get 2 products because you've got partial charges and partial bonds, and it's hard to know where everything is. So let's just react the 2 resonance structures. And we've done this a lot. A lot. Sometimes correctly, sometimes not. So if I do that, I'm going to get those 2 products. So then the question becomes, which one is the kinetic product, which one is the thermodynamic product? Aaron?
The left one would be only the kinetic. It would have stable.
So you want the left one to be the kinetic product?
Yeah.
Everybody agree with him? There's some people. So if I'm looking at that left carbocation, what kind is it? Secondary. What's the one on the right? Secondary. Which one's more stable? Well, why would the one on the left be more stable than the one on the right? Or vice versa, if they're both secondary. Okay, the position of double bond. I'll go down that road with you. So then we look, because to be honest with you, you could have a secondary carbocation with a double bond that's more or less substituted that might play into that. So let's test that out. So how many alkyl groups are attached to the double bond on the left? 2. How many on the right? Is there any stability difference between those? So we have a problem. What? No magic. It's all sleight of hand. I got two intermediates that are the same, that basically have the same stability according to our rules, right? What?
Is there any
Yeah, this. Well, rearrangement meaning a hydrogen shift or something? Because rearrangement, we've used that term to indicate that we have a shift. That's different than a resonance structure, because in a resonance structure you can't break bonds. So if you're saying that going from this intermediate or this resonance structure to this one is a rearrangement, that's technically not what it is. It's forming the resonance structure.
So if you wanted to figure out which one was most stable.
Well, in our rules right now, they have the same stability, right? Sarah?
Wait, what were you saying about the stability of the double bonds? The carbocation is secondary,
So let's say I had one. Let's say it would have left off the methyl group. Why won't you erase? Let's say it would have left off the methyl group. So I would have that other methyl group. So I would have ended up with a plus chart. I would have ended up with that plus, and this wouldn't have made any sense, right? Because that would be primary versus secondary.
Right.
But let's say, I don't know, let's say I did that.
Okay.
And let's say I did that. So I'm comparing these two carbocations. I've got secondary versus secondary. They're tied, right?
Yeah.
But the one on the right, or one on the left has a double bond with one alkyl group, and the middle one has a double bond with two alkyl groups.
So you're looking at how substituted it is?
But I'm looking at that as a secondary characteristic.
Okay.
The first characteristic is the carbocation, whether it's primary, secondary, or tertiary. But when I'm tied, I could look at the double bond and say, oh, well, this is double bond's more stable. So this overall would be more stable than the one on the left. Now, I don't have that here, right? But if I had this kind of situation, I could make the case that the one I circled is more stable because it's got a more stable double bond. But my first criteria is carbocations. Then look at the double bond. So that's an example of, I don't know where that example would come into play, but it might. Well, I do, it's just in the future. All right, so where are we at? Oh, we have the same energy for the intermediate. And how about the product? Same energy there. We agree on that? That the intermediate has the same energy, both intermediates and both products have the same energy. Now, this doesn't happen very often. But what does this mean?
There's two major products.
It means you've got two major products. It means you have two major products under what conditions? All conditions. So if there's no more stable carbocation and no product that's more stable, then what that means is that whatever percentage of those two products I get at 1 hour reaction, I'm going to get the same at 24-hour reaction. I'm going to get at minus 80 degrees or 100 degrees. The idea of kinetic and thermodynamic products is if I switch the conditions, I switch the major product percentage. I make it go from one to the other. If that doesn't happen, there is really no kinetic or thermodynamic product.
So it would be 50-50.
So it would probably be near 50-50 under all conditions. And so there would not be a kinetic product and there would not be a thermodynamic product, because that's what those terms mean. And those are boring, right? Because there's nothing I can do to make one the major product or the other one the major product. So this is kind of a unique reaction, which I wouldn't necessarily give you because it's boring. except in the fact that up until 10 minutes ago, we didn't know what to do when we had equal stabilities of reactants or of intermediates and products. But that's what this means. So this cyclohexane, if you did 1,2,1,4 addition, adding HCl to that cyclohexane, that would be another example where there's no kinetic and there's no thermodynamic product. Because let's just do that real quick. So I've got my numbering scheme, my 1, 2. So I'm going to put a hydrogen on 1, chlorine on 2, double bond between 2 and 3. Put a hydrogen on 1, put the chlorine on 4, move the double bond between 2 and 3. The double bond, the first one is between 3 and 4. Okay. So when you understand the 1, 2, 1, 4 products, and you know what the electrophile and you know what the nucleophile is, you can write the products that quickly. So now if I'm looking at those two products, which one's the major product? Well, I can't use that term anymore, can I? I've got to say, is it which one's the kinetic, which one's the thermodynamic product? And in this case, those two products are the same. These two products are the same. And you might say, well, why can't I erase? Get rid of the hydrogens. Or if not, don't focus on the hydrogens. What do you got? You got a chlorine attached to an allylic carbon in both cases. Same, name them. What would that be? That'd be 1, 2, 3. That'd be 3-chlorocyclohexene. Same product. Well, if you form the same product, there's no kinetic and there's no thermodynamic products. Because singular product does not equal products with an S. Vinny?
How'd you guys put it on 2 and 4 again?
Well, I first put it on 1 and 2 and left 3 and 4 the same. And then I put it on 1 and 4, and then the double bond has to move between 2 and 3. Right? That's what happens down here. Right? The double bond moves between 3 and 4 into between 2 and 3. Okay. So, and this probably wasn't the best one to start with because there's no kinetic, no thermodynamic product. But we got to deal with it sometime, right? What happens? Because somebody would have asked me, can you have a reaction where there is no kinetic or there is no thermodynamic product? Well, I've given you now 2 examples before the test, right? Because normally you'd ask me that and I'd say, well, that's a good question. I'll have to find one of those for the test. Does this make sense to everybody? So we have really simple rules. Our simple rules are, you look at the carbocation and you compare. And you compare primary, secondary, tertiary. So secondary, tied, double bond, 2 alkyl groups, tied. That's as far as our rules go, because it didn't matter what was attached to the secondary carbocation, they're all the same, whether it's methyl, ethyl, isopropyl, etc. So let's see. Let me make a change to this molecule, because usually, let's see, I can make a couple of changes to this molecule. Usually if I make one change to it, I can completely change the problem. Right, so let's see. How do we want to do this? Oh. Because here's what I have. I got a couple of options here. I'll add 2 methyl groups. Are you sure? Are you sure that they're the same? Or, shouldn't be giving away all of the tricks, I could put 2 methyl groups there. Now do I have a distinctly different kinetic and thermodynamic products? Are they different? Well, the only way to find out is to do it. Is to add HCl to each one of these. So my first step would be 1, 2, 3, 4. 1, 2, 3, 4. And since I've concluded that I've mastered writing the mechanisms for this, which I would conclude, you could conclude that yourself, but I'll have to verify that. Let's just say, okay, H, Cl. So there is my 1, 2 product. And what would my 1, 4 product look like? Add H to carbon 1, move the double bond between 2 and 3, and now add the Cl over there. So there's my 2 products from the molecule on the left. Do we have a kinetic product? A single kinetic product?
Yeah.
I hear 2 yeses. Any others? Three. Anybody else? Anybody stuck? Okay. What do you need? What information do you need to tell me if we have a single kinetic product? The intermediates. So I don't have those. So that's why you're stuck. Okay? So since I took the easy way out, just wrote the products and didn't write the intermediates, oh no, I don't know what to do about my kinetic product. Okay, fine. Let's work backwards. So where did the plus charges go? Where the chlorine attached. So down here, what I can then do is I can say, okay, let me write the intermediate because what I do know is this. I know that wherever the chlorine attached, it attached to a carbocation. So there's intermediate 1 for 1, 2, and here comes intermediate. There's intermediate 2 for 1, the 1, 4 intermediate. Okay. So how did we get there? We got there by taking the chlorine and adding to the carbocation. So if all I have is the product, what can I do? I'd erase the chlorine and put a plus charge there, and I've got my intermediate. Does that make sense to everybody? Because what I'm actually doing is I'm giving you a couple different ways to write the mechanism. If you can see that it's really easy to do 1, 2, 1, 4, but you're struggling with the carbocations, that's okay. Write the 1, 2, 1, 4 product and erase the chlorines, and you've got the carbocation. The resonance hybrid, well, we're probably going to need some help on that if you don't quite see how to do that. Okay, so now we got both. So do we have a single kinetic product? Yes, and what is it? The one on the right or one on the left? The 1,4 would be the kinetic product. So 1,4 would be kinetic in this case. Okay? Because it's coming from a tertiary carbocation. And the 1,2 product is coming from a secondary. Right. So what's the thermodynamic product? It's going to be the 1,2, right? Now, can you normally just say, that's the other one? You know, most of the time you can. Most of the time it is going to be the other one, except if you have those two molecules we started with, where there is no kinetic and there is no thermodynamic. So you're better off to check. So I look, I see 3 alkyl groups to double bond. I see 2 alkyl groups to double bond. Yes, that's the thermodynamic product on the left. Okay. So you can write the mechanism either way. You can write the mechanism by adding the electrophile to carbon 1, having the allylic carbocation, drawing a resonance structure, and then adding chlorines to the carbocations. But if you're better at 1,2, 1,4, do that, and then erase the chlorines or bromines or whatever they are, and that'll give you the carbocation intermediates. Okay. Make sense? Questions? No? We got plenty of time. Try that one. And I wouldn't have any assumptions about, oh, well, that means it's going to be opposite. I don't know. Just go ahead and write those, and write the intermediates, final products, and then you can tell me which one is kinetic and which one is thermodynamic. 1,2 versus 1,4. so we'll have to. No, that's good. Sometimes I'm surprised. Okay, there's my two molecules with a 1, 2, 3, and a 4. What did you add to it? You add HCl, since I didn't really tell you what to add to it.
Yeah.
Okay. Okay, where you want the HCl to go? Where you want the H to go? H goes on 1. In both cases? Okay, where's the Cl going to go? 2. 4, where's the double bond going to go? And, okay, there's my two products. Okay. Which one's kinetic? Top one's kinetic. Bottom one's thermodynamic? Okay. Anybody have any issues with that? That's what you got? That's what you would have gotten if you had more time?
So the hydrogen will never add to anything other than carbon 1, which is the nucleophile that moves through.
Right. Right. So the electrophile, and remember, we have other electrophiles. I could add Br2 to this. So the Br plus would add to carbon 1. And when I mean carbon 1, I mean carbon 1 or carbon 4, depending on whether you want to go left or right. So you're correct. Yes, H will only add to carbon 1, and then the chlorine will add to either carbon 2 or carbon 4. And that's the beauty of the 1,2,1,4 system, is that it literally lays out exactly where the two groups are going to add.
So if you add the Cl to the to 4, does the double bond always go to 2, 3?
Yes. Yes, it always has to migrate. If it doesn't, I got 5 bonds to that carbon, which isn't going to work. Sarah?
Can I go over an example of adding Br2?
Sure. Okay, so we're good with this? Okay, sure, we can go Br2. Yeah, as far as I can tell, you're right. Now, you would have had to write you most likely would have had to write the carbocations and the resonance hybrid. Or if I give this to you as a problem in writing products, I'll say specifically either give me the kinetic and the thermodynamic products in 2 different boxes, or I'll say what would be the major product at minus 80 degrees for an hour. Low temperature, short reaction time. Right? So then you have to make the connection. Oh, those are kinetic conditions. Now I got to find the kinetic product. Right? Doing a Br2 is exactly the same. So if I wanted to, we'll do this one. So if I wanted to add Br2 to this, I'm going to treat the Br plus just as a Br plus. I'm not going to worry about having the bromonium ion. I'm just going to treat it as a Br plus. So I'm going to say, okay, I'm going to add my Br to carbon 1. That's going to leave me a carbocation. Then I'm going to write the resonance hybrid or resonance structure. And then I'm going to add my Br minus to both those. So here I'm not concerned about the triangular bromonium ion. I'm just concerned about adding the two BRs. So in this case, the two BRs add 1, 2. And over here, the two BRs add 1, 4. So there really isn't much of a difference.
You would need light, wouldn't you?
But
You would need light, wouldn't you?
no. Is that in one of the videos? NBS? Do you know what NBS is? So this would happen without light.
You need an example with VR2 without light. It just did.
Okay, so this would happen with or without light. First, everybody okay with this?
Like, as in,
Hold on. Let's just deal with this first, and then we'll deal with this complication. So we're okay with that, and then we just figure out which one's kinetic, which one's thermodynamic. So the critical part is you don't treat bromonium. You don't have a bromonium ion. You just treat the Br as Br plus. In the problems for Friday, I've given you H plus H2O. When you have H plus H2O, what do? You add H plus, and then you add the entire water molecule to the carbocation, right?
Yeah.
So it's going to take an extra step, but you can handle it. You just have to remember to do it. Okay. So there's an issue. So if I said, hey, add Br2 to this molecule, and you said, well, light or dark, under light, no light, or heat, right? So I do this reaction with light. At room temperature, I do it with heat, or I do it with no light. I'm going to get that product. And notice that's not conjugated diene. Okay. So I'm going to get that product regardless. Because bromine, to try and do free radical halogenation, the bromine would have to split apart. Well, the bromine doesn't have to split apart. It sees a double bond, it adds with a Br plus and a Br minus. So this is a problem. Because before, when we've wanted to do free radical halogenation, we've never had to worry about bromine adding to a double bond. So now if I said, well, no, I want to actually add the bromine by free radical halogenation to the allylic position, what do I have to do? I can't use bromine. I can't use liquid bromine. So that's where we have this reagent called NBS, N-bromosuccinimide. And so N-bromosuccinimide breaks down. It doesn't have Br2 in it. It breaks down so that NBS is the equivalent of a bromine radical. And so then the bromine radical starts the process of doing free radical halogenation and substituting an H for a Br. So we're going to have to be careful when we do free radical halogenations from now on. Because if we're trying to do them with a double bond, they won't work. They'll just add two BRs.
You said we can't do that because you want it to be allylic.
Well, if I add any molecular bromine to any molecule with the double bond, it does electrophilic addition. It adds the two bromines. It doesn't have time to do free radical halogenation. probably, if I had 2 vials sitting over by the window, because the sunlight, which isn't out there now, it's being filtered through by 5 layers of clouds and snow. Maybe in May, just before we finish, we'll have sunshine, we can do that. But if I took an alkene and I took an alkane and I added bromine to it, the bromine with the alkene, the red color of bromine would be gone instantly. The red color with the alkane would eventually disappear because eventually it would react with the light, the sunlight, to form a free radical reaction.
I'm gonna bring that up in the studies we do.
What?
I'm gonna bring that up in the studies we do.
Man, remind me when we have a day where we have nothing else to do.
Could you then also do this reaction with NBS under extreme conditions?
You could actually from now on, you can use NBS to do any free radical halogenation. So you could react NBS with pentane and make you just tell me whether it's at room temperature or high temperature.
So you can do it at 300 degrees to get those statistics.
Yeah, you probably wouldn't,
Okay.
because that would destroy the succinimide. So that was something in the video. We got to be careful now when we want to do free radical halogenation. It's NBS. Sam?
So add 2 bromines or bromine and hydrogen? What did you say? Bromine and hydrogen? Or something?
The NBS?
Yeah.
The NBS substituted this hydrogen with that bromine by a free radical mechanism.
Oh, okay.
Right? Initiation, propagation, termination. Okay. Sarah?
So at the top when you wrote plus BR2, you technically meant NBS.
No, I meant if I do this if I want to go from here to here, let's make this more complicated than it needs to be. So if I want to go from here to here, I need only NBS. Only NBS. If I try and do anything other than NBS, so I try light and room temperature, or I try heat, or I try no light, I add 2 bromines across the double bond. Okay. All right. Video for Friday is, I think it's released, as is the online quiz. If it's not, I'll see if I can do that in the next hour. What's due on Friday, online quiz for the video for Friday, and then this practice problem set.
So under what conditions do you get this?
NBS only.
How
It's
is it?
NBS and heat or whatever it is, but it's just NBS.
But why
NBS
is it choosing that position?
because why is it choosing that position?
Yeah.
Because that's allylic and there's a resonance structure to it.
Oh.
I think that was in the video too, wasn't it? You might have to go back and look at it.